See what happens. So no go here. So let's make V2 1. So coming back here, if I make V2 1, let's see if we can solve the remaining equation. 4V1 over square root of V1 squared plus what? 1 must equal 3. All right. That looks a little better, I think, because I'm not going to get the V1s to cancel, right? Now I have to solve this equation. And believe it or not, I did this in my college algebra class the other day, yesterday. Something like this. If you replace all the V1s with X's, this is just solving some sort of rational equation with some square roots in it and stuff. You're just trying to solve for X. So we clear the fractions out and square both sides of the equation, and we go to town. Let's see what happens. So how about this? This the same? That's the same? Okay. Let's square both sides of the equation right now to get rid of the root on the right side. So I'll get 16V1, 9 times V1 squared plus 1. With me still? Did I forget squared? Yes, I did. Did I say squared? I thought I said squared. And then 16V1 squared equals 9V1 squared plus 9. What type of equation is that? Don't be shy. It's quadratic, right? So subtract 9V1 squared from both sides. And divide through by 7. And we get two potential answers here, don't we? Plus or minus square root of top and bottom, so 3 over root 7. So I have two possible answers for V1. Understand this? So here's what I think V should be. I think V should be the vector. My V1, I'm going to pick the positive. What was V2? 1, and my V3 was 0. I think that if you project U onto that vector, it will have a length of 3. Do you feel like checking? I do. Okay, let's project it. So I need the component of U onto V right now. That's dot these two together, right? The dot should go pretty clean, right? What's the dot going to be? 4 times this, 0 times 1, negative 1 times 0. So it's just going to be 4 times this, right? Which is 12 over root 7 over the magnitude of, what was the formula? Magnitude of what? I'm projecting onto V, so it's V, right? So what is the length of V? It's the square root of this squared. What's this squared? 9/7 plus this squared. 1, but 1 is the same as 7/7. So that's what? 16/7? So 12 over root 7 over 16 over 7 root, which is the same as 4 over root 7. Flip it, 3. Check. That's right. Y'all see it? Okay. Feel better about that. Is that the only answer? No. There's an infinite number of answers. I found 2. I found 2 of them. I could have used this or negative, right? This. So how would you have got a different answer?
Switch one of the variables.
Maybe you let V3 be 0 and V2 be 2. That took way too long. Okay, good. We're at the end. Now, I believe that's the homework assignment. I don't know if that's accurate with what's on what I put online. The homework sets that I put online for Chapter 10 are official. So if this is off a little bit, then don't worry about it. But there's no such thing as doing too many homework problems, all right? There's no such thing. Never heard that before. 10.4 is where we go now. All right, remember me saying that there were 3 types of multiplication when it comes to vectors, right? 3 types. First one is scalar multiplication. Second one, dot product. Take 2 vectors, dot them together, you get a number. And now you have finally the cross product. So remember with the notation, if we are writing a vector u in 2-dimensional spaces, u1, u2, we can also write it as u1i hat plus u2j hat, right? And then if we have a vector in 3-dimensional space, we can do u1i hat plus u2j hat plus u3k hat. Just remember that. Dot product gives us a number, right? We define now, this should say third type, but a lot of people don't look at scalar multiplication as a multiplication of vectors. Because there's only 2 ways to multiply vectors together. There's dot product and cross product. The one restriction for this new product, this cross product, is that your vectors must be in 3-dimensional space. They have to be in R3 in order to do a cross product. Now you might say, well, that sucks. How are we going to, then what do you do in R2? We do have a workaround, okay? We do have a way of getting around it if we're in R2. But for now, let's just assume that your vectors are in R3. So let's say that we have 2 vectors, u and v, and we want to do a cross product. We use this cross in between the 2 vectors. And then there's a formula for how to compute it. And I don't know anybody who really memorizes that formula, because it's kind of a pain in the ass to memorize. Instead, there is a short way of doing it, all right? So what I'd like to do is, I think if I just show you by example, then that'll be the easiest way for you to learn how to do a cross product. All right, so here are 2 vectors, all right? U and v, and I want to cross u and v. So what I'm going to do is I'm going to write the vector u down first, and I'm going to use angle brackets. Okay, that's the vector u. And I want to cross it with v, right? So I'm going to put the vector v below it vertically, all right? Below it, like this. And then I'm going to do the following. My answer, u crossed with v, will be equal to a new vector, okay? So when you cross 2 vectors together, do a cross product, you get a new answer, you get a vector as an answer. Now we'll talk about what it means geometrically in a minute, but let's just see how you mechanically get the answer. So my answer, since it's a vector, it has 3 components, doesn't it? It has an I component, a j component, and a k component, or a first component, second component, third component. The way that you get the first component, the I component, is by coming over to this, covering up these 2. So you cover up the first components here, and you do what's called a determinant. So if you did any matrices, you may recall this thing called a determinant. Show of hands, determinant? Okay, so a lot of you haven't seen determinant, that's fine. Don't worry about the word determinant, just follow what I'm about to do. So if we're doing the I, I'm going to put I up above here to kind of remind you, this is the I component, this is the j, this is the k, right? Those are the components of the vector. If I'm trying to find the I component, I come over here and I hide the I components here with my arm. And then I look at these 4 numbers right here, and I do the following multiplication. I do this number times this number, which is what? Negative 3 times negative 3. I'll actually write it out. Negative 3 times 3, right? I'm going to do that. And then I do this one times this one. Remember, this is covered up, which is negative 1 times 5, which is negative 5. So negative 1 times 5. But you subtract. So let me run through that again. This times this minus this times this. This times this minus this times this. Not the other way around. It's not this times this minus this times this. And that's what the determinant is. If you go look it up, that's what a determinant is. It's this little, there's a formula for it. But the pattern is the most important thing for us. Here to here minus here to here. What is that answer? What is it? Negative 9 plus 5. So negative 4. That goes here. With me? Now, if we're going to now try and find the j component, what do you think you're going to do here? Cover up the j column, and do the determinant on the 4 numbers that you can still see there. So what am I going to multiply together first? 2 times 3 minus 4 times 5, right? Now hold on. Not that simple. 2 times 3 minus, what was it? 4 times 5. So you would think that your answer is what? 6 take away 20, which would be, what's 6 minus 20? Minus 14? But when you're doing the j component, you have to change the sign of that answer. It's only for the j. You do the same computation, but whatever your answer is, change the sign. So if we get negative 14, I'm actually going to put what here? Positive 14. So put a little note there for yourself. You know, don't forget, right there, change sign. Right, this one up here was negative 4. This one up here was negative 14, but we changed the sign, positive 14. And then the last one, if we're going to get the k, we're going to cover k up, right? Cover the k column up, and do the determinant on these 4 numbers, and this one you won't have to change the sign. So what? Negative 2 times negative 1 minus 4 times negative 3. Is that what I did? 2 times negative 1 minus 4 times negative 3. What's that? 10. And you do not change the sign. Now you will get, if you've never done cross products before, you will get, faster and faster with these as time goes on. Just be careful. You don't want to forget that negative part. Or you don't want to accidentally cover up the wrong column. You're trying to find the I over here, and you come over here and cover up k for some reason. Just be careful. Now there's like 4 or 5 different ways you can show people to do cross products, and that's just, that's just the way that I'm going to show it to you. There's other ways. Anyone seen something different? Yeah, what have you seen?
We did it using this, but then he drew a wheel, and it's like you cross I and j, you get a positive, and j and k get a positive, and then I and k, it's like something like that.
So it was a wheel?
Yeah.
Okay. I've seen it where you write these down, like 2, negative 3, 5, and then you write it down again, 2, negative 3, 5, and then 4, negative 1, 3, and then 4, negative 1, 3. Oops. And then I, j, k, I, j, k. And then you do these like diagonals and then go backwards. Have you all seen that before? Okay, so there's like all these different ways of doing it. Your calculators can do it. A lot of your calculators have built-in function called cross on it, and it can do a cross product. If you have a TI-89 or a TI-86, I think the 86s do it also, it has the built-in feature. But you should be able to do it by hand, all right? So that was our answer, right? I just erased it. Wonderful, I just erased it. What was it? Negative 4, 14, 10. And that was U cross V, wasn't it? Now, what would be the difference if I did V cross U? Is it the same? Yeah, if you do it the way I just showed you, the 4, negative 1, 3 would be the one on top, right? And the one on the bottom would be 2, negative 3, and 5. Right? And so you would still go through the same thing. You'd cover and do that thing. And if you did it, your answer would turn out to be 4, negative 14, negative 10. Which means what? They're not the same, right? They're not the same, but they are what? They're opposites. They're parallel. They're actually pointed in the opposite direction. You could even write this. U cross V is equal to negative V cross U. Just remember, U cross V is a vector, right? And so if I scale it by negative, that's what the cross the other way would be. So when I cross two vectors, one direction, I get that vector. If I cross them the other direction, it's parallel, but it's pointed the opposite way. Okay? All right, so I know some of you have done cross products, so I'm curious if anyone knows visually what the cross product is. Can anyone explain to the class? If I have two vectors and I cross them, it's a perpendicular vector to what? To what plane? You're on the right track. So I've got a vector here, right? Let's call this U. I've got a vector here, call it V. If we put them tail to tail, right? There's U, there's V, yes? When I cross these two vectors together, when I do a cross product, I get a third vector. That vector is perpendicular to both of these. That's what it'll be. It'll be a new vector. What's that?
Isn't it the normal vector?
Not exactly. We reserve that for planes. Yes and no. We don't call this one a normal. Okay, so you see this? They do kind of create a sheet, right? These two vectors, like a sheet. So when I take these and cross them, and I cross U and V together, I get a third vector which is orthogonal to both. Okay, I just scaled V by 1/4. Okay? All right, so this vector is now orthogonal to both. Yes? If I cross them the other direction, it's this vector, but what? Coming out the bottom. Yes? And it follows the right-hand rule. So if I cross U with V, my fingers go from U, right hand, U, curl towards V, the cross product vector will come out the direction of my thumb. If I cross V with U, I have to turn my hand upside down and go V to U, then the cross product comes out the other side. Understand? Now that's the best I can do with rulers and markers. This is it visually. This is I think harder to see. As good as a computer can be, it's still difficult to put three-dimensional space on a flat sheet. So this is something, if you were at home, you could mess with this if you downloaded this program. The red and the blue vectors are like U and V, and the black vector is their cross product. So hopefully by looking at this you can agree that if I turn this appropriately, it looks like the black vector is perpendicular to the blue. And if I turn the other way, hopefully you agree that it is also perpendicular to the red. And this is a major, major result, all right? That's what I put on here. We often use cross products when we are trying to find a vector that is perpendicular to two other vectors. A lot of times we will have two vectors and we will have the need to find a vector that's perpendicular to both. Anytime you need to do that, you bring the cross product in. So here's an example. Let U be 2, negative 3, 5, and V be 4, negative 3, 1. Show that the cross product, U cross V, is orthogonal to U and to V. So I just told you it's going to be orthogonal, right? I just told you that if you take two vectors and cross them, that cross product is orthogonal to both. This is an example where I want you to prove that that's true. So let's first start by finding the cross product of these. What is the cross product of these two vectors? Well, did we just do that one? No, we didn't, did we? Is it? Yeah, it's the same vectors, right? I do that intentionally so we don't have to keep doing the same like these computations over and over. So we already did that example just a second ago, and we found the cross product. What was it? Was negative 4? No. Negative 4, 14, and 10. I want us to show that that cross product is orthogonal to u. So how would you show me that that's orthogonal to u? Dot it with u, right? So how about we take this cross product and we dot it with u. What would you, oh, that's bad. Dot product's not a vector. What would you get? Or what are you doing to do this? You're doing 4 times 2, right? 14 times negative 3, 10 times 5, right? And we should get 0, shouldn't we? Negative 8. What's that? Plus negative 52, 42. And then plus 50. And that's 0. So that means that the cross product vector that we created is orthogonal to u. Now just show it's orthogonal to v also. So show that u cross v dotted with v is 0. So do this with this one. What do we have? So negative 16 plus negative 14 plus 30, which is 0. And so that's not a coincidence. That is the actual property of a cross product. It will always be orthogonal to both the vectors you started with. Questions? Show that for any vector, non-zero vector, well, I guess it would work for the zero vector also. Show that if you cross a vector with itself, you get 0. So you want to cross a vector with itself real quick? See what happens? Let's define u to be a three-dimensional vector, u1, u2, u3. If I'm going to cross it with itself, I'm going to write it vertically like this, right? And then I'm going to do this little thing over here where I cover things up. So what is u crossed with u? We have 3 components, don't we? The first component you get by covering up what? The first columns, right? This right here. And then doing your little determinant there. So let's do that. What would we get? u2 times u3 minus u2 times u3. Same thing, which is 0. And then if we're going to get the j, we cover up j, and we do our little thing, and it'll be u1 times u3 minus u1 times u3, which is 0, and then change the sign. 0 is still the negative 0, right? So that's 0. And then the last one would be the same thing. And that is the 0 vector, isn't it? So if you cross a vector with itself, you get the 0 vector. Questions? Now we get into some good stuff. All right. I'm giving us 3 points, and I want you to find a vector, any vector, I don't care what it is, that is perpendicular to the plane that passes through those 3 points. So we have 3 points sitting in space, right? Let's call them A, B, and C. I could, if I want, connect those 3 points with lines, right? And once you have 3 points in three-dimensional space, they should define a plane, shouldn't they? Like, you know how you need 2 points to define a straight line, right? You need 3 distinct points to define a plane. So once I have 3 distinct points, I've got a plane here, don't I? I want you to take that plane, which is sitting somewhere. I don't know how it's oriented. It's not necessarily flat or this way, or, I mean, it could be anywhere, right? I want you to give me a vector that's popping out of that thing that's perpendicular to it. So how could you give me a vector, any vector you could think of that would pop out of that plane and be perpendicular to the plane? How could you do it? Find vectors, 2 vectors from these points, and then cross them.
But they have to be perpendicular
To each other?
on the triangle.
If I take, let's label this A, B, and C. If I take this vector right here, the vector AB, and I take the vector that goes from A to C, then regardless of the angle between them, see if I can keep these vectors from falling apart.
So we still stick out.
If we have 2 vectors, it doesn't matter what the angle between them is. If I cross these 2 together, I'm guaranteed a 3rd vector that's orthogonal to both, right? And that would be orthogonal to the plane that they pass through. So all we need to do, correct, is just get 2 vectors on that plane and cross them. Now, could I have done other vectors? Could I have done the vector from C to B? Yes. So what would, if I do it as I did up here, what's the vector AB? So from A to B, -3, 1, -7? Other way. We're going A to B. You'll get it. You'll get it. A to C is what? 0, -5, -5. Okay, just quick show of hands. We agree with this? These 2 vectors? Yes? Okay. Now what do we do with them? Cross them. Well, I kind of wrote them vertically on purpose, because now I'm going to cross right here. So I'm going to do AB cross with AC. The answer will go right here. So I cover up the eyes, and I do my little thing right here. So let's do that one right here. 1 times -5 is minus, what's the next one? -5 times -7. So what is that number? Are you getting?
-35.
Negative. What's -5 and -7? Positive 35, but then subtract it. -30, -40. This whole thing should be -40. Right? What's wrong? What's wrong? Y'all okay? Did I do that okay? Yes? Yes, subtract. Okay, so you just got to be careful with these signs, right? What about the middle one? So this and this is what? 15. So -3 and -5. Then minus 0 times -7 is 0. So I get what? 15? But then change the sign. So -15. And then finally, Cover up this one. What? 15, take away 0, so just 15. There we go. That vector should be perpendicular to my plane. Any questions on that? Could I do this? Could, check it how? Check it with, dot it with what? Yes, you could dot this with this and then this with this to verify it. But that's the whole kind of point of the cross product, is that if you do it right, you're guaranteed that. But if you just want to see, make sure, then yes. Now this vector is perpendicular to my plane, right? So it's sticking out of my plane like this. Could I have used this as an answer? Could I have used that? Yes, why? That's just a scalar multiple of this, isn't it? All I did is divided each of these by -5, right? Divide that by -5, divide that by -5, divide that by -5, and you get that vector. So that vector is pointed in the same direction as this one, isn't it? Well, actually, sorry, it's parallel. It's shorter, isn't it? And pointed in the opposite direction. So instead of sticking out of my plane like this, it's going into the plane, going off the other side. But that's okay, because all the instructions said is to find a vector perpendicular to the plane. So originally we found like this one, and then we divided it by 5 and flipped it over. So now it's on the other side, and it's 1/5 as long on the other side, pointing out. Questions on that? Got about 10 minutes left. All right, do you remember there was a theorem for the dot product? That the dot product of u and v was magnitude of u times magnitude of v times cosine of the angle between them, right? Well, there's a similar theorem for the cross product. It's very similar, except what are the differences? It's sine theta, right? And it's not just the cross product, it's what? It's the magnitude of it, right? So remember, the cross product gives you a vector, right? The length of that vector is the length of u times the length of v times sine of the angle between the two vectors. I don't think this one's worth going through. Find the magnitude of the cross product if someone gives you the length of the two vectors and the angle. I'll write it up here, but what is it going to be? It's going to be 3 times 7 times sine of 31 degrees, right? That's just using the formula from right before. They give you all the information, the lengths and then the angles, so that's not... All right, here's another result. Remember I talked about if and only if statements last time? We said that if the dot product is 0, then they're perpendicular vectors. If they're perpendicular vectors, then the dot product is 0, both ways. We have another if and only if statement here. Two non-zero vectors. If the vectors are parallel, then the cross product is 0, is the 0 vector. If the cross product of two vectors is the 0 vector, then they are parallel vectors. So this is a check to see if vectors are parallel. Now for us, it's how have we been checking to see if two vectors are parallel? Just multiples of each other, which I would say is probably easier than this. But this is a theorem, it's here. If we needed it, we could use it. You know, obviously, if I write two vectors up here and say, are they parallel, you're going to start looking to see if you can scale it, right? You're not going to start taking the cross product and seeing if it's the 0 vector. Now, there is a geometric meaning to the magnitude of the cross product, and this is really kind of cool. If you were to take, again, two vectors and cross them, right? Right-hand rule, You get this vector that sticks out that's perpendicular, right? The length of that vector has meaning to it. How long that vector is that's sticking out has meaning to it. The meaning of the vector is this. It is the area of the parallelogram formed by the two vectors. So I have a ooh, that's not working. Come on. I thought I had some initial settings here that were, yeah. Sorry, I should have had this set up before I came into class. There we go. So I'll zoom in on this so we can see it. Okay, so we have a red vector, and red, that's black. Black vector and a red vector, right? If I take these two vectors and I cross them, I get a vector that pops out. This green one is the vector that pops out, and it is orthogonal. Do y'all see that that green one is orthogonal? Kind of? There, that's a little better. Okay, so cross it, vectors. That's way off the page, it's very long. What the length of that vector represents is, imagine creating a parallelogram out of these two vectors. So it's like taking these two vectors that are sitting here and constructing the parallelogram out of them. And the area of that parallelogram is the length of that vector. And that's pretty awesome. Because we can do a problem like this. This problem would be virtually, not totally, but very, very difficult without what we just talked about. This will be the last thing I'm going to be able to do. Find the area of a triangle with these vertices. Are those the same 3 points that we had earlier? They are? They are, right? Same 3 points. What's the area of that triangle? Is that the way I drew it, though? I don't remember drawing it that way. I think I drew it like this. I think I did something more like this. Did I do this A, B, and C? Isn't that what I had? Okay. How am I going to find the area of this triangle? Imagine just if you walked in today, or you walked in first day of class, said, hey, here's 3 points in 3-dimensional space. Find the area of the triangle created by those. That'd be a challenging problem. Right, because wouldn't you, you'd be probably thinking, okay, I'm going to need the base and the height, right? Which means you would need to somehow get like the distance from here to here, and that'd be very hard in 3-dimensional space to figure out what that is. But what does the previous note say that we can do? Does anyone see this? I hear, but I didn't see who said it.
Use the magnitude of A, B, B, C, and multiply by the sine of A.
So you're wanting me to look at this cross product, right? Obviously, the magnitude of the cross product. You're wanting me to look at this? What does the magnitude of the cross product represent geometrically? The area of the parallelogram, right? Formed by those two vectors. So if we come back over here and we look at this example we did earlier, we created this vector AB, didn't we? We created this vector AC. And the reason we did that is because we were trying to find a vector that came out of this, right? Yes? And we did find that, didn't we? We crossed these two together. We did AB crossed with AC, and we found -40, -15, +15. And that was the cross product of those two vectors, yes? If I take the magnitude of this and the magnitude of this, right, which is the magnitude of that, that represents the area of the parallelogram formed by those two vectors. Now let me show you the parallelogram formed by those two vectors. It's that, right? And so I don't want this, if I'm trying to find the area of the triangle, I want half of that parallelogram, don't I? So this area will be half of this. Understand? So the area here will be equal to half of the magnitude of AB crossed with AC. Now that's how you find an area of a triangle in three-dimensional space. That's easy to do. So how would you get this magnitude? Well, square root of this squared plus this squared plus this squared, that's a number, right? Divide it by 2, that's the area. Do I need to go through it, or you think you can handle that? Think you can handle that? Now, if you go, I don't know if y'all have been looking at your take-home exam at all. Have you all been looking at those? Let's just look at, I know we're out of time, but let's see what I would say you can handle at this point. Now, on the first day I handed these out and I didn't have copies for everyone. The people who I didn't have copies for, were you able to get your own copies? Anyone still need a copy of this? Everyone's good? You do need it? It's online. It's in, yeah, didn't I post it or did I send it in an email?
It's online.
It's online. It's in the exams. There's like a folder that says exams. All right, I would expect at this point you could do number 1. Yeah, you could do number 1. That's not a stretch, okay? Number 2 can also be done. Please pay attention. Oh, you know what? Does yours say vectors on this regular pentagon? Does it say that on yours?
No.
It doesn't? Put regular pentagon. Believe it or not, that matters.
All sides are equal.
That's right. All sides are equal.
And it's opposed. Sorry.
And you can also assume something else here. That you can assume that that's a right angle. It's implied, but just to be clear, it is a right angle. Pardon me? U equals V? You can assume the magnitude of U equals the magnitude of V. That you can assume. Number 3 can be done. But I will tell you on this problem, you are not to use a computer or a calculator to solve this. This should be done by hand, and what I'm interested in seeing is whether or not you have a way of solving what you're going to have to solve here. And if you're running into problems like I have no idea how to solve something like that, then you should get with me. Okay, I'd be happy. The whole point is that I want to make sure everyone here knows how to solve the equation that results in here. Right? And if you don't, then it's a pretty quick technique. A parallel pipet has these corners. Find the length of the diagonal. You could do that at this point. You could find the length of the diagonal. That's the length of, from the point here to the far corner of the parallel pipet. Parallel pipet is a three-dimensional solid. Find the angle between the vectors. You could do that. Finding the volume of the solid we haven't talked about yet. This one, this is a tetrahedron, three-dimensional. And you should be able to solve this now. You should be able to do that. This one we have not talked about. Sorry I kept you over a little bit. Y'all get out of here. Is that it? Have a good weekend? Right? That's where we are? Do your homework at least through 10.3. Get through 10.3 homework. Excuse me, I'm just going to turn off my camera real quick. Make sure.
This fucking compartment right here.